So for building a data warehouse, I had several SQL engines that run on top of data stored on HDFS that I could have used. However, I chose Spark SQL because we are very used to working with Spark, and also we invested in an open source project for this ecosystem. So for those of you who don't know, Spark SQL, it's one of Spark's modules that is used for processing structures, for analyzing and processing structured data. So Spark SQL supports several input formats like files stored in Parquet or JSON, or maybe data stored in Hive tables where the data stays on HDFS and the schema stays in the Hive metastore. Also, it supports already existing RDDs or data stored in external databases like Cassandra, data that is retrieved through JDBC. After retrieving the data from several input formats, Spark SQL stores this data into a distributed collection called the data frame, or the former schema RDD for those of you who are more familiar with previous versions of Spark. To work with Spark SQL, you can write your code in either Java, Scala, or Python, or you can execute SQL commands on top of the Spark SQL context. Okay, so now we have the data ingested and transformed, and it's stored in memory in Tachyon in a CSV file format. So we will want to query it. To query it, we will have to create that distributed collection that I mentioned before, which is a data frame. To create it, we will have to first read the schema and then read the data. To read the schema, we can read the text file from memory. Then we will have to split it after comma. As I said, it's a comma-separated file. And we will map each field into a struct field that will create the struct type storing the schema. To read the data, we do the same thing. We read the text file, split it after comma, and then map each data row into a Spark SQL row inside an RDD. So having the schema in a struct type and the data into an RDD of rows, we can create the data frame on top of the Spark SQL context. We can use this data frame in order to query the data stored on Tachyon. So to do this, we either could use the built-in methods on top of the data frame. Here is a simple example of a group by using the already implemented method. Or you can register your data frame into a temporary table and execute a standard SQL command on top of it. However, this is quite difficult. You won't want to do this each time your session is recreated. So you won't want to map your data into a table each time and split it after comma and so on. You will want to somehow share these transformations between sessions. And you can do this either executing a SQL command on top of a Hive context. As you can see here, I have a Hive context. The Hive context extends the Spark SQL context and adds the functionality of operating with data stored in Hive. You can do this, and you share the data between sessions, or you can save your data frame as a table. What happens here is the fact that you have your data into a Spark SQL table, but you have the schema stored in the Hive metastore. But as I said before, we want to build a in-memory data pipeline. So Radu ingested the files in memory, transformed them in memory. So what I would like to do is to build a warehouse on top of data stored in memory. So what I would do is to write the files in Parquet format inside Tachyon. So I could do this with the following command: data frame save as Parquet file. However, this won't work. It won't work because I'm executing the driver from a machine that doesn't have a Tachyon worker on it. So if I do that, it will fail while writing the schema. Andrei, you met him before, he open sourced a project that fixes this issue by sending the code execution to the workers. So for the job that I wrote to export the data in Tachyon in Parquet file format, I have used his code. You can take it from GitHub, or you can download it from the Maven public repo because it was already published there. So, file formats. There are several file formats that we use in different pipelines. However, we favor Parquet because it has a set of benefits. Being a columnar format, it's very good for aggregation queries, and it's really cool because only the required columns are read from the disk and not the entire row. It also supports nested data structures, and what's really important is the fact that you have the schema stored with the data. So what does this mean? You won't need to have an external meta store to store your schema for your file, because always the schema will be there. Parquet with Spark SQL, it's really awesome because Spark SQL supports schema evolutions on files stored in Parquet format. What does this mean? If you have a table that has a column A, let's say, and you add another file there with a field from a column B, Spark SQL will know how to merge them in order to obtain a table having also the column A and the column B, which is quite cool. And the most important thing is the fact that Parquet files support efficient compression and encoding schemes, as they can be specified per column. And if there's something that I've learned while working with files in memory is the fact that the footprint of your data, it's more important than the compression and decompression speed, because spilling your data to disk will always be more expensive than quite slower decompression algorithm. So it's something that you will have to balance this battle between disk I/O and CPU. Of course, it depends on the size of your data, it depends on the resources you have on your cluster. I mentioned about Tachyon, so I will have to explain what it is. It's a distributed file system that stores the data in memory. So what Tachyon does really nice is the fact that he avoids going to disk each time you have to read some data from a data set that you frequently use. And it avoids going to disk by keeping it in memory. And because it is in memory, it allows different frameworks that run on the same cluster to access the same data with the in-memory speed, which you don't have otherwise. Tachyon has a pluggable underlayer file system that could be either HDFS, S3, ClusterFS, whatever fits you best. So he makes checkpoints on the underlayer file system. However, you have other ways of keeping your data in memory. The other alternative you have is caching it in Spark SQL. You can do this by calling the cache table method on top of your context, or you can call the cache method on top of the data frame you had before, or you can execute a SQL command, a SQL statement on top of your Hive context. It doesn't matter which of these methods you choose to cache your data, because Spark Cache will store the data in a columnar format in memory, and will automatically fine-tune the compression in order to minimize the pressure on your memory. But having Spark Cache, why do we encourage you to use Tachyon? Well, there are a set of reasons. The first one is that the Spark JVM sometimes might crash, and it does crash. And if it does crash, you will lose the memory you will lose the data from memory. Using Tachyon, you won't deal with this because the data will be outside the Spark JVM. So if Spark dies, you will still have the data in memory. Usually, Spark Cache will outperform Tachyon. It's better, it's faster. But however, sometimes Spark SQL JVM will encounter garbage collection. And if it does, the queries will take longer. You don't have this problem when using Tachyon because the data will be stored off-heap into the RAM disk. And in these cases, we have seen Tachyon outperform Spark Cache. But remember only when your data is really large and the garbage collection kicks in because of the memory pressure. And the most important thing is the fact that we can share the same data with the in-memory speed between different applications. So we are not forced to build a huge application to do them all. You can have different specialized microservices to do smaller parts of your computation, which is good. Okay, the last thing I want to speak about is Spark Job Rest. It's an open source project that I have worked on. In fact, it's a data warehouse that is scalable and resilient, which allows you to submit concurrently and asynchronously submit queries, Spark SQL queries. Actually, it's an alternative to the Spark SQL JDBC, but it has an interactive UI and it has a set of features that you don't have in the Spark SQL JDBC. JAWS has quite a history. I started working on it since Spark 091. Back then, it didn't exist Spark SQL. We worked on Shark. Now we support Spark SQL, and also we can execute Hive commands on top of Hadoop MapReduce. So we have the possibility, offer the possibility to run queries on Spark or on Hadoop. JAWS is built upon an ACA actor system, which means which makes it possible to support query cancellation. What do I mean? You can deploy, for resiliency reasons, you can deploy different instances of JAWS on different machines. And if you want to cancel a query, you might have a problem because the cancel request might end up on a Spark context that didn't trigger the query, so it won't know how to cancel it. But having the ACA actor system behind, when a cancel request ends up on an instance, the ACA actors will send this message to all the deployed instances, so the context that triggered the query will know that it has to cancel, which is quite important. The next features I will describe in a live demo. The code that we used for this pipeline, all the jobs, the ingestion, the transformation, and the export, it's on GitHub. You can take a look there. Okay. So this is JAWS UI. You can see here the query history, what I have run. You can see the logs for a query, and you can see the results. What's really important about these results is the fact that we support retrieving huge amount of results, which is not possible in Spark SQL JDBC because it will crash your driver without that memory. We managed to do this by storing the results already on Tachyon in memory or on HDFS, and we store it by zipping it with an index in order to be able to filter it when retrieving it. So this is something that you don't have with the Spark JDBC. As you can see here, when running a query, you can select either to store this huge amount of results on HDFS or on Tachyon. Okay. Here you can browse through the databases. These databases are stored in Hive through the tables inside the database. And what else do we have? It's the possibility of creating and querying tables that are stored in Parquet. Parquet files stored either on HDFS or on Tachyon. We have here a file browser that browses the files on Tachyon. Here is the output of my job that exported the files in Tachyon in Parquet files. Okay. These are the files. We can map this directory into a table. This table is created and then we should be able to see it under the Parquet tables. Okay, we can see the fields inside it. So now we can run a query. Let's say we want to run a select count everything number, and let's say we will group by site. And we will run it. Query is running, the logs appear, and you have the results. I performed a group by site on top of financial transactions. Okay. I mentioned about Tachyon. This is how Tachyon looks like. It's just like a normal file system, but it's in memory. This was the folder that I showed you before. If we go inside it, you will see that all the Parquet files are stored in memory 100%. You can see the underlayer file system, which is HDFS, and also you can see the IPs of the machines that store each file from there. Okay. So this is Tachyon. As you mentioned, yeah, we are using Mesos as a resource manager. As you can see here, there are several completed frameworks, several completed Spark contexts that finished work, finished their job. Somewhere here there is the right Parquet file job that it's finished. I ran it yesterday. The files are still in memory because I used them. And what I wanted to show you by this is the fact that it doesn't matter that the application that created the files, the Parquet files, is dead and buried. It doesn't matter that the context is dead. You can still benefit from the fact that you can query the data really fast with the in-memory speed. Okay, and I think that's it. Here you can find the code. These are the 3 jobs that I mentioned. And also you can find the project. In GitHub, you have a full readme file explaining all the APIs. You have a configuration file that allows you to set all the Spark properties in order to obtain the best benefits of running your project. So if you have questions for either me or Radu, please.
Can you tell me a little bit more about the Tachyon serialization strategy? What's the window of risk that I have storing data in Tachyon before I start making sure that they're serialized in HDFS or some other Tachyon store? How is my data at risk?
Your data is not at risk at all because Tachyon is always backed up by HDFS or one of the other file systems.
I understand that, but how often does it do the actual write?
When you upload the file in Tachyon, it's also stored on disk.
Is it synchronous or?
Yeah. Asynchronous. Yeah, and when you configure Tachyon, you set up a memory for it. And when this memory exceeds, when you upload in memory too much data, then the least used data set will be evicted from the memory. And if you start using them once again, they will be read.
That's for read caching rather than write caching.
Sorry?
That's for read caching
for read,
rather than write caching.
For read. Yes, but I wanted to let you know the fact that when the memory exceeds, it is evicted. So you're safe, but it's stored on your underlayer file system.
So what's the difference between HDFS caching and Tachyon? I know the HDFS caching is a newer feature.
The HDFS caching is
a newer feature.
It's a newer feature. I don't think I didn't know.
HDFS caching, you need special support in the client to do that.
But they are already using Tachyon right as a caching layer, so they're specifying.
No, I'm saying that Tachyon is, if you specify Tachyon as a file system, you get caching automatically from
HDFS.
Tachyon, right? HDFS, to get the HDFS cache, you have to ask for it.
Alright, anyways.
It's correct to say that the persistence of data from Mesos is achieved through Tachyon.
The persistence of
The
data
persistence from Mesos, it's achieved with Tachyon.
You are referring to the example that I gave before.
Yes.
Maybe it is confusing. Mesos only acts as a resource manager. So it only spreads the core between the application running on the same cluster. What I wanted there to show you is the fact that the application it's dead, but you still can benefit from the fact that the files are in memory. So the Tachyon and Mesos are not related.
So how do you said